Okay, so with that, let's get started with our Atom Probe analysis. So the Atom Probe Toolbox installing is actually very, very easy. So all you need to do is double click on the Atom Probe Toolbox sign, and your add-on manager will come up with a window showing you, do you want to see the getting started guide? And yes, we want to see that, because I will just quickly talk about that. And then we have the Atom Probe Toolbox installed. It says version 0.9 because we still will do a little bit of bug fixing, but everything is pretty stable already by now. Okay, so if you want to see the contents of the toolbox, by the way, you can go into your program files, Matlab, release, whatever release you have. I hope you have. Oops, and I forgot to switch over to here, but I guess you all were able to install it. It's not a very difficult thing to do. And then here you should have all your different toolboxes. And I don't know why the Atom Probe Toolbox is not here. Anyway, it is usable. Maybe is there a user toolbox version? Anyway, I should have looked into that a little bit deeper. You will be able to find it if you really need to. If you want to look at the code by itself, you can go onto my GitHub. So there's a GitHub under my name, where you will find the Atom Probe Toolbox. And the difference between this and what you have now is this is the active code we are working on. So this is always the latest and greatest, but it might differ slightly from what's in the toolbox already. The reason for that is not that we're changing the functionality, so this is actually pretty solid by now. But we do have a lot more Atom Probe code than what is in the toolbox. What is in the toolbox is already migrated, so it's already adapted to our analysis system, and it's well documented. If you want to be in for a little bit of a wilder ride, you can go on to the Atom Probe code section, where we have a lot more code. But this code is not always up to date with using tables in Matlab and using our arranging system and so on and so forth. But with a little bit of knowledge, actually not that much knowledge, you are going to be able to use that as well. Good, so what you find here is a lot of interface analysis stuff, interfacial access maps, things like that we haven't migrated yet, but will migrate in the near future. But you can already use it. Feel free to use it. Also, feel free to use the code. So if you want to do your own things, feel free to use the code. We are always happy if people are contributing to our toolbox. So if you think you have made something in Matlab that could fit into the toolbox, please contact us and we will include it into the toolbox. Obviously, with a copyright notice that it's not our code, but that it's your code. And if there is a publication about it, if you wrote a publication about it, we would obviously also put in a DOE for the publication so people can cite your publication. All right, so what is actually the deal with the Atom Probe Toolbox? And the most important deal about it is that okay. The most important deal about it is that we want analysis to be flexible and interoperable. So we want to have a fair toolbox. So we want to have our our analysis to be flexible and interoperable. And this is one very important thing. So what we wanted to do with this toolbox is really to give you a basis that you can work off of, sort of a platform you can work off of, and hopefully use it with a lot of different with a lot of different kinds of analysis systems. So we'll use it with Python, use it in conjunction with R, use it in conjunction with anything that's anything that is compiled. We want it to be modular, so we want it to be in a way that you can script your own analysis and you can add your own analysis. So not just what we have given you, but also you can add to it. And this is also indescriptible. Then we want it to be lean and maintainable. So we are going to be using Matlab's built-in functionality to its maximum capability, so that we can minimize the amount of code that we need to maintain, and that also we take the most advantage of anything that MathWorks adds to Matlab. And with every release, there is some really helpful things that are being added. The biggest release for us though was release 2015B. That's when tables came in, and also categorical arrays, which we are going to be using heavily. Then we want it to be explorable, so you should be able to explore all the data and all the code to its full depth. Okay. Then obviously we want it to be customizable, so you should be able to customize the analysis to your needs. And by that, for example, we mean that you have your own color schemes, you can have your own isotope tables if you do isotopic experiments, and so on and so forth. We want it to be efficient and reproducible. So that means that the toolbox should be efficient in workflows also for large data sets and large and complex geometry, and that all of the information can be retrieved, saved and retrieved in a very accessible way. And you will see that the easiest way to save your analysis in this case is just in Matlab. You can save your entire workspace, and then you can just take off where you stopped. And we want it to be learnable. And learnable means that you are presented with a system that gives you the ability to learn how to use the toolbox. And a lot of that is based on Livescripts. Yeah. It's based on Livescripts, and you're already seeing the getting started Livescript. And I'll show you in a second what Livescripts are. But the most important Livescripts that we have are our workflows. So I told you that we are going to be working based on command line commands. That doesn't mean that you're always going to be sitting here with the command window typing things into a command window, but this is obviously the most explorable way of doing things. But you will be building up analysis, and you can take that analysis and put it in scripts. And Livescripts. Livescripts are scripts where you can combine code with explanations to the code, and you can turn that easily into PDFs, Word files, and so on and so forth, so that if you run your analysis on your first data set, you have a lot of work. On the second data set, you can use the Livescript from the first data set, and you can just save it as a report, for example, things like that. And we've provided you with quite a few different workflows. I'm not going to go through each individual ones because we have 3 days for that. And we're working off of what we called ground truths. And there is actually 3. The third one is sort of a half ground truth. And the ground truth means we have some universal truths that we're using as the basis of our analysis. And these are the color scheme. Color scheme, of course, is not a ground truth in the sense of that it's some physical thing that you absolutely need to know. But essentially, the color scheme is what you put into your analysis that will determine all of the coloring. If you change your color scheme, obviously you can rerun your analysis and everything will pop up with the right color. And especially if you work with certain material systems, which is the case for most of us, then you will probably come up with a nice color scheme for your material system that is hopefully in such a way that if you do visualization of different elements that they are not too similarly colored, and also ideally that they are catering to the colorblind, that it's made sure that colorblind people can see things properly, and so on and so forth. If you Google color scheme, there's a couple of tools out on the web that can build color schemes for you, where you can just take the RGB values from those color schemes and maybe type it into a color scheme. We will give you a default color scheme, which is just one that I've created randomly, which works okay for a lot of purposes, but probably for your own purpose you want to adapt that. The next thing we have is the isotope table, and I should probably already load that in. And I need to test that FAU. So okay, usually I work off of the thing here. Okay, so how do I get to the isotope? Oh, thanks, Valentin. By the way, all of the code that we are using here, I will send to everyone via the Zoom chat. So if you want to get the no, not to Valentin, to everyone in the meeting. So you can load the isotope table natural abundances, and then you will get the isotope table here. And you can already see the isotope table means that we just have atomic number, element, isotope, weight, abundance, and atomic density. This is already filled out by us according to the International Chemistry Association to the IUPAC natural abundances of the individual isotopes. And what you can already see here is that we have a table structure. Yeah? So I hope you all familiarized yourself with Matlab a little bit. If not, tables are essentially arrays where each array column can be a different type and you can index into them. Okay, so let me just undock that so that it's a floating window. And in that isotope table, I can, for example, go and say isotope table let's say, I don't know, isotope table I want the 5th row and all entries, and that would be lithium 6, and it will have the weight, the abundance, and the atomic density. But I can and you can see the I can also index by name. So I can go isotope table dot and then use the tab key to get the autocomplete, and I can see, okay, I can look at abundance, element, isotope, and so on and so forth. And we will use those tables quite a lot. So if, for example, I wanted to see isotope table, everything that's lithium, I can go and do a truth in an indexing into that. Isotope table dot element equals, I don't know, let's go for iron because I do a lot of steel stuff. And I want all entries there, and then you see we'll get the four iron isotopes. And this is really the power of using tables. And one thing I've already done here as well is using categorical arrays. So you can also Google Google Categorical Arrays. Out of my way. And categorical arrays just means you have arrays that have individual categories, for example, RGB, GB, or whatever that thing here is. In our case here, our categories are very often the chemical elements. Yeah? So if I, for example, go into the isotope table variable, I could go here and click on here and you can see I've got all the chemical elements here. And I can create a new one. And this is, for example, important if we do isotope analysis and we want to highlight a certain isotope. Then you would change the name from whatever its element is to whatever you want, maybe tracer or whatever you want to call it. Okay. And the next thing we want to load is our color scheme. So we can go load. What is the color scheme? Load color scheme.mat, and you can see. By the way, autocomplete in Matlab is just a tab key. So if I wrote load col, then I got all kinds of options, and you can see, for example, this is probably from Valentin, who's got a color scheme for his hard codings. Yeah. And in the color scheme, if I go into the color scheme, you can see here that we just have names for the ions and the colors that are associated with them. And you can also have complex ions. And here, it's actually very important for us that we have the ability to use names for our ions, and for that I will just quickly explain to you how our ion naming works. I think it's relatively straightforward. So oops, no. File. So essentially, if you have an ion, then you have various ways to write that ion, and this will be very consistent throughout our toolbox. Basically, this will be, if you have an element, you just write the element as is. Yeah? If you have a complex ion, then if you have a molecule, then you have put a space between them. Yeah? So, for example, iron oxide. If you have something where you have two elements of one, so where you have two atoms of one element, then it would, for example, be FeO2. Yeah? If you would like to be specific about what isotope it is, then the isotopic number comes before the element symbol. So for example, if I want to be specific that I only want to look at iron oxide where the oxygen is oxygen 18, then I can say iron 18 oxygen 2, for example. Yeah. If I want to be specific that it's iron 18 oxygen 16 oxygen, then I would write it like this. Yeah. And on top of that, if I would like it to be specific about the charge state, then it would be iron 18 oxygen 16 oxygen space plus plus, okay? And we will have that quite a lot throughout the toolbox, okay? So this is how we write down which ions we're talking about or which elements we're talking about. Good. And so here for the coloring, we don't usually use charge states and we don't usually use isotopes. But I think there's not anything that really would keep you from doing that. But for now, we've done the coloring just based on the ion itself or the element. You usually get the ability to work either with the ions as ions or with the ions as ions decomposed in the individual atoms. Okay, which brings us to the last ground truth, which is the ion list. And so the ion list is a list of potential ions in your data set. So you can see here, this is one that my student Martina has actually made for her aluminium data set. And you can see that it's all ordered by mass to charge, and then what ion it is and what ion it is in an isotopic way. So you just saw the writing that I showed you before. So here, for example, at 17.9867, we would have silicon 30, 24 magnesium 3+. If that's realistic or not is not the question right now, but this is something we could use to search whether that ion exists. And Martina will show you in the next session how to do that. So this is actually an ion list that is produced based on which elements we suspect to be in the material. But we also have an ion list that is curated, which means that some of my students, especially my student assistant, one of my student assistants has gone through the Atom Probe literature and just looked up what ions people have seen. And so we have an entire, my student assistant Teresa Fuchs has done that. And Teresa has gone through the through a large part of the Atom Probe literature already, and just collected which ions people have seen in their data sets. And so you can go and also search based on that. But very often, like we go in unbiased and just say, okay, we have these elements in there, build me a list of all possible ions I could get from those, and then we can go through our mass spectrum and see if they're actually there or not. Great, so these are our ground truths, and these are the basis. These are essentially the basis that we work off of. With that, we will just then go and just load in a data set. So the loaders we use right now are made for Kamika systems, which means if you have a LEAP system, you will have either POS or EPOS files that you can load in. And we turn them into a table, and that table is the basis you work off of. We also have loaders for ATO that I haven't migrated yet to the new format. If one of you is using an older Kamika Atom Probe and wants to use the ATO format, then let us know. Also, if you've got any kinds of wishes of things that you think are not there that should be there, or that you might need for your work right now and that are maybe in the that we have coded already and it's in the Atom Probe code but not in the toolbox, then let us know and we can work with you and move it up the ladder quickly. If you have your own data format, for example, we have a home built Atom Probe as well, which has a different data format. Then you can usually use the import data function in Matlab, which is very good to get data out of all kinds of different formats. It just auto detects what's in there to the best of its ability, and then you can very often load your data in as well. If not, we can work on file loaders. What we work with extensively is the HDF5 file format, which I'm not going to introduce right now because we've got an entire session on that, and that is, I think, right now the most convenient way to store your data. And Markus Kübach just writes there's a reader for the new APT file format for Matlab and Python. Yeah, that is very nice, and we will obviously take that. Great thank you to Markus. We will take your reader and make it possible also to to read in the new AP Suite 6 file format into our system. All right, it's actually very simple. So all you need to do is assign a variable, and I usually use pos equals read pos. Sorry, I'm still used to the very old one. Pos to table, yeah, pos to table, and then always use the semicolon to suppress the output, because if you've got a long data file, it will print like God knows how many columns into your into a workspace. Then you have to choose epos. Unfortunately, Matlab doesn't let you select multiple different options. I don't know why. And I believe the aluminium new would be the one that we're going to be working off of. But for now, I'm just going to show you what's in the file. And you can see right now it's still loading. It's a relatively large data set. I think it's a pretty nice data set. And once that's done, we can just easily open it. I think everything's a little bit slower right now on my computer here, just simply because I've got OBS and the streaming and everything running. That slows stuff down a little bit. Yeah, so the file aluminium new epos is loaded, and I've assigned it to the variable pos. And you will see that during the entire course of my analysis, very often I try to be as consistent as possible with variable naming. The reason for that is that if I do that, I can be very fast with autocomplete. So I can use autocomplete a lot, and it makes for very, very fast working. Okay, and now we've got our pos file here, and I can just click on it, and you can see it's very descriptive. So we've got the ion index. So what ion that is, which is very important when later we go and split the ions, the complex ions up. So right now this is obviously just a running number. Then we've got the reconstructed X, Y, and Z positions. And if you click on the little arrow here, you will see that the unit is nanometers. So we also have defined the units, which is very important, because I remember the first time I started doing my own analysis on ATO files, I wasn't quite aware that they were using kilovolts and meters and so on and so forth. Then we've got the master charge here, and obviously if you click, you can see it's in Daltons. Then we have the time of flight, DC voltage, pulse voltage, detector X, detector Y, delta P, multiplicity, and atom number. Yeah. And this is essentially all of the information that you have in an EPOS file. And now the upside that we have here is that you can index using dot indexing, and I'll show you in a second how to do that, to use dot indexing to work with the individual fields, which makes it much easier if things are not in the same order. So if you always load Chemica POS or EPOS files, it will always be in the same order. But if you load files from our Oxcart atom probe or from the atom probes that Inspico makes in Stuttgart, you might have different orders, but as long as you consistently call things, you will not have a problem. Yeah? So as long as the X, Y, and Z are called X, Y, and Z, VDC is called VDC, and so on and so forth, that will all be fine. And with that, we can actually already do some nice and neat things. So for example, this is a relatively long data set, so I think that's what 22 million atoms. But one thing you can also do is look up how large the files are in terms of size, and what you will see is that Matlab is very, very, very memory efficient. So I've heard very often people say that Matlab is not very fast. It's usually because people are used to programming in C or languages where loops are very prevalent. MATLAB is very much array based. If you go for loops, that makes it a little bit, that can make it a little bit slow. But it's also very memory efficient. So I think you're gonna have a very hard time keeping up with the hordes of programmers at MathWorks that are making sure that this is all very efficient. And you can see here we've got bytes, kilobytes, megabytes. So you can see we have 23 megabytes or 2 megabytes. Did I scroll past? I think it's 2 megabytes. So it's very, very, very memory efficient. Yeah. Anyway, so one very simple thing I can do already in this case is, for example, crop only the first maybe 1 million atoms. Yeah, I can do that very easily. I can call that variable maybe pos crop, and that pos crop would be pos 1 to 1 million, and we want to have all entries. Yeah. And now I have a second variable, and you can see, okay, this variable now has 1 million entries, and these 1 million entries are cropped by essentially evaporation sequence, right? So this is a very simple way to crop by evaporation sequence. But we could also just crop by z coordinate or by x coordinate or by y coordinate, and that is something we would do by, for example, I just override the old variable. We're not doing anything with it anyway, and in this case it would be indexing into pos dot z maybe is larger than, or let's say less than 100, and pos.z is larger than 90. So this would be a 10 nanometer slice, and we want to have all entries from that. And you can see our pos crop is now, I don't know, probably 195,000 or something like that. So about 200,000 atoms, about 200,000 hits. And so these are very simple things you can already do with the, you can already do just based on the pos variable. And I think we all had situations where we maybe wanted to crop by evaporation sequence or something like that, and that is very simple to do. Thank you, Martina, for putting in my my code lines. I've totally forgotten about that I was supposed to do that. Okay, so at that I'll just ask you, I see that there's some people having problems loading. Can you just give me a green tick if you were able to load in some pos data? Okay, so I see some green ticks, so I hope everyone was able to do that. Good. But obviously, if we just look at the pos file, just looking at a okay, we so some people have a problem with the atom number. Are you possibly on Linux? Okay, that's weird because people here are using Windows 10 as well. Yeah, so obviously the simplest way to fix that is just use the hashtag or remove the hashtag or the number, the pound sign from the code, and then you should be fine. Sorry about that. It definitely, It's the usual programmer answer. It works on my machine, right? It works on our machines. Obviously, there is some kind of it might be a language thing, or so if you have. Okay, that's a weird one. We've never had that error before, but it's definitely something we will note down. And I should probably just then open a bug tracker. So, okay, how do I open the script from the toolbox? Because usually I have not worked off of the toolbox yet. Open post to table. Thank you. So we give you we obviously give you a troubleshooting guide already. This was totally planned because we wanted to show you how to fix something. Anyway, so if you go, sorry, I'll jump back into the command window. Open post to table. And if you have that open, at some point at the bottom, it will try to assign the variable names. And the atom number, just remove the pound sign from the atom number. So I hope all of you have seen that. If you remove the pound sign here, then you should get rid of that problem. So let me just load the data again so that that's changed. Okay, yes, so I think the question you had is you have to click here and select EPOS. Yeah. And select EPOS. So unfortunately, Matlab is also case sensitive. So if your EPOS file extension is with capital E, then it will still be grayed out. So you have to change it to lowercase EPOS, which is a bit annoying, but this is one of the things that Matlab still has. It is lowercase. Okay. Everyone else has an EPOS file loaded. Can I get a green tick from everyone that has an EPOS file loaded? So I definitely want to see a lot of green. And can I maybe get a red one from people that have tried to load an EPOS file and haven't managed to? Oh, sure. So if you go into the script, it's on this line here, so line 93. Line 93, and at the end it says atom and then pound sign. And I've removed the pound sign, okay? This was the issue here. Okay, so Renel is so far the only red one I see. Okay. Maybe Renee, you can ask one of our helpers, like Martina or Valentin, that can maybe work with you and get the script working for you. Okay, with that, let's then move to displaying a mass spectrum. So if we want to display a mass spectrum, we have a convenience function for that, and that is called plot mass spectrum. Okay, and I'll show you the help file for it first. Oh no, it's called mass spec plot by now. Sorry, mass spec plot, and thank you, David, for posting the as code. And what you can see here is that we can choose what bin size or what variable we want to use, or what pos file we want to use, what pos variable we want to use, what bin size we want to have, and then we can either have it as a count mass spectrum, so that we go by count, or normalized. And the default mode is count. So essentially, if we compare different mass spectra, we usually go for a normalized mode. And if we go and want to, for example, count how many atoms are in a mass spectrum of a certain kind, we usually go by count mode. And what we need in the end, we need the handle, and that's a graphics handle, and we'll get to graphics handles in a second. And the graphics handle will be what we use to refer to the mass spectrum later on. Okay, so if we do a lot of different analysis, we will use the mass spectrum handle to do the analysis later on. And I usually will call the mass spectrum spec, and that will then be mass spec plot. And the mass spec plot will be based on our pos file, our pos variable. You could also just use a vector that stands for individual master charge values. Then we will use a bin size, and usually a pretty okay bin size of 1/100th of a Dalton, depends on the dataset size. You will see if you change the bin size, how the mass spectrum change. So essentially, if you use a very narrow bin size, it will look a bit noisy. If you use too wide a bin size, then you will miss out on some details. That the question might arise, what is an optimum in this case? And the thing is, as with all histograms, there is no optimum. Yeah, histograms do not have an optimum. You have to make a decision about how fine-grained your histogram should be. And by now, we will go by count. If you don't write anything, it will also go by count. And what we will get is a Matlab figure that is our mass spectrum, and that contains some additional information as well. So you're all very familiar with that. So by default, we've set the zooming to just zoom in the X direction, because that's mostly what you do. You can also use the mouse wheel to do that. And also, if you click on the hand will allow you to pan. If you do right click, you can go from the restricted to the unrestricted. So if I go zooming, right click, I can do a vertical zoom or unrestricted, or restore view, and so on and so forth. And you can already see we've got our individual peaks here, and probably 1/100th of a Dalton was not a bad choice. You also get some statistics here. And thank you for Benedict for posting that. You can see some statistics in the background. So you can see, okay, the bin width. So when you save that, this will be saved with your mass spectrum, and you can see, okay, there is about 100th of a Dalton bin size. In the whole thing, we've got about 23 million atoms. And at 4 Daltons, we have a background of 164 ppm per Dalton. The reason why the background is measured at 4 Dalton is because usually here not much is happening. If you have H4, or if you work with deuterium and you've got D2 and so on, or you might have helium for some reason, you might have a peak at 4, then this is obviously not as meaningful. But for quite a lot of mass spectra, this just gives you a very quick look of how high your background is. And 164 ppm per Dalton is pretty okay. So ppm meaning compared, so if you took a range here that's 1 Dalton wide, that would be 164 ppm of all of the hits in the entire mass spectrum. Okay, this is what that means. And here, this is actually an aluminium data set that Martina sent out to all of you, and you will be able to work with that later on. So what I will next show you then is how we set up these things here, and with no in-depth explanation. So generally, we have a Matlab figure here that has a figure hierarchy. And our spec, our variable spec that you can see here, is an area plot. This is a handle. So this is essentially a variable that represents the mass spectrum plot. And it refers specifically to this plot here. It does not refer to the figure, and it also does not refer to the axis. It refers to this plot here. And this becomes important when we start reloading our mass spectrum. So once we start ranging and everything, we might want to save that figure, and all of our information about the ranging will be contained in this figure. And if we then later want to refer to the mass spectrum, we need to refer to this mass spectrum plot. So you might now say, okay, why don't we refer to the axis as the mass spectrum plot? Or why don't we refer to the figure as the mass spectrum plot? And the reason is very simply that very often, if we have more complex data sets, we want to compare individual mass spectra. So we can have ranges that span different mass spectra. So you can have 2 or 3 mass spectra in here, but define ranges that apply to all of those different mass spectra. Especially if you're doing electronic materials, multi-layers, and so on and so forth, this is incredibly helpful. But this this means that you need to be aware that the mass spectrum refers specifically to the mass spectrum plot. And the mass spectrum plot is part of the Matlab graphics system hierarchy, which we have here. And the Matlab graphics system hierarchy works by having child-parent relationships. So our mass spectrum here is a child to the axis it exists in. And the axis it exists in is a child to the Matlab figure it exists in. And that Matlab figure is a child to the Matlab graphics root object. We will not be doing anything with the Matlab graphics root object, but we will be doing stuff with the figure, we will be doing stuff with the axis, and we will be doing stuff with various objects in that axis and their relationship. And this is what I meant by we will be making use of the Matlab built-in capabilities as much as possible by using the properties of these graphics objects. And I can actually have a look at these properties very easily by just clicking here on the property inspector. And you can see here, okay, we have this axis and we have the mass spectrum here. And the reason why it knows how to call it it's called mass spectra is because that mass spectrum, if we go back into the code, has properties. So we can go spec dot and then press autocomplete. And you can see we have all kinds of different properties. I can, for example, change the face color. So maybe I want to have the background of it red. And so I can just use 1, 0, 0. So this is red, green, blue colors. So all of our colors will be RGB colors. So red, green, blue, and from 0 to 1. So 1 means completely red, If I now press that, then you will see that miraculously the background color of our plot is now red. And I can do that with a whole lot of different properties. So if I go and autocomplete, you can see I have a whole lot of different properties that I can adapt. And this is really the power of using a system like Matlab, is that all of that is already here for you, right? So I can, for example, go, okay, we changed the face color. I could change the edge color meaning the line color, or I could change the transparency. I could do all kinds of things. Yeah? And one thing I can do is go and find out what parents. So Matlab always starts in capital letters, and I can show what parents we have. So our mass spectrum has a parent, and that parent is the axis that we're in. Okay. And you can see that in the hierarchy here, that okay, the parent is the axis, and then we've got another parent called mass spectrum, which is the figure. And the reason why it says mass spectrum here is because there's one property called display name that we use a lot, and the display name is called mass spectrum. Yeah? And you can change that display name if you've got multiple mass spectra. Obviously, you don't want to call all of them mass spectrum. You might want to call one mass spectrum different than the other mass spectrum. Yeah. But this is all very explorable. You can always go into the property inspector, and you can see the parent here. And if there were any children, you can see, you would be able to see the children here. Obviously, our mass spectrum plot doesn't have any children. But our axis obviously does have children. And you can change all kinds of things here. And one thing that's very important for us, if in all of our objects, is the user data. Yeah? And the user data right now only has one field, and that is the plot type, and the plot type is mass spectrum. So if you write code that goes into that mass spectrum plot and wants to find out which object is the mass spectrum, then you can search for any object that has a user data dot plot type that is mass spectrum. Yeah, so I could write user data and then autocomplete again. There's only one type of user data, which is plot type. Yeah, and that is mass spectrum. And so thanks for my helpers for posting the for posting the code. So it turns out it's it's a bit hard to do both things at the same time. Yeah. And this is what we can do with our Matlab graphics objects, because we will have a lot of graphics objects in here that actually carry data. So we will have ranges, we will have ion definitions, and we'll have various labels that we can put into our mass spectrum plot that we're actually going to be working with. Okay, so there will be a lot of things that are in there. And let me just change the color again. So the face color is gray, so that's maybe 0.5, 0.5, 0.5. And now we're back. Oh, that's a little bit of a dark gray. So we maybe will make it 0.7, 0.7, 0.7. And now we can see we've got a nice gray again for our mass spectrum. Okay, this is so these graphic objects, they will appear quite a lot throughout our analysis. And you will see that they can be very rich in information. And I will just show you right now what a mass spec figure will look like. So here, this is one that you will be making in the next session with Martina as your host. Martina Heller as your host. And you can see here already, we've got a mass spectrum with all kinds of ions defined. And all kinds of ranges defined. So you can see here, we've got manganese, we've got aluminium hydride, we've got zinc, we've got vanadium, chromium, and so on and so forth. And we also have magnesium and so on and so forth. So it's an aluminium alloy. And what you can see here is that you have ranges and you have ion definitions. So the circles are standing for the ion definitions. And you can see here, for example, we've got chromium, and we've got one peak here, for example, that doesn't have an associated range because this is aluminium. Yeah, this is mostly aluminium in this peak, and only very, very little chromium. Yeah. And Martina will show you in the next session how to prepare something like this. Yeah. But this is essentially what your mass spectra will look like, and then you can go and save it, and save it as a figure, and both programmatically load it in or also load it in just as a figure again. And I'm showing you this just simply because if you want to work with that mass spectrum, what you will need to do then is to click on on the spectral part of it, and then it will just go that your spectrum is your current object. So GCO stands for get current object. So it now loaded in, so it now assigned this mass spectrum here to our variable spec. And this is what we will work with. Then you can do funny things like, I don't know, range table equals range table extract from mass spectrum. And don't worry too much about that right now. But this is, for example, how we will get our ranges out, right? So this will all exist in this figure, graphically, and we can very easily pull it out. And when you want to delete a range, what you literally do is just delete the graphics object. Or if you want to delete an ion, then you will just create that. So right now you don't need to worry about what file I'm working with. I'm just showing you things. Yeah, Martina in the next session will actually show you how to properly create something like this. And I can then use that to create a plot of various elements in various ways, and this just popped up in a way that now great. This was not very size-wise. Okay, with different size screens, it always pops up in Windows pop up in weird ways. Yeah. So here then we would have the silicon and the magnesium in this data set displayed. And then you can, do everything that you're used to, rotate stuff around. We usually plot things in multiple windows, and we have those windows connected so that they're always the same orientation, and you can do nice animations. And one thing you can already see is that maybe the color scheme is not quite optimal because you can't see the difference between the silicon and the magnesium all that well. Because they're almost the same color. But this is easily fixable. You can just go into the color scheme and change that. Okay, so the last thing I want to show you in this session is then how Livescripts work, because we are going to be heavily using Livescripts. And the good thing about Livescripts is really they sort of give you the best in between a graphical user interface and scripting. So what Livescripts are is essentially what a lot of people would call, are familiar with as some kind of programming notebook. It was really popularized in Python by Jupyter Notebooks, and this here is actually very similar to it. And Actually, Markus Kübach on Friday will show you how to use Jupyter notebooks to do your analysis. So if you jump over to Python, you will find it very, very similar. And with that, I actually want to take maybe some of the resilience out of people in using multiple programming languages, because people always are under the impression that learning a new programming language is kind of similar to learning a new language. It's very much not. Learning a new programming language is more or less like learning how to drive a different car. It's more like you know roughly where the steering wheel is, you know where the where the shift is, or maybe you're moving from a manual to an automatic gearbox, but you in principle know how to drive a car. And it's very similar with programming languages. Once you've learned one, it's easier to learn others. And Markus just very nicely wrote, a language is not a tool. What we really need to be focused on is what kind of tools we want to use, and they might be in different languages, and we want to give you the ability to work with the different tools in the different languages. But I got sidetracked a little bit now, so let's go to the live scripts. And so what a live script is really a combination of graphics, text, and code. Yeah? So you can combine graphics, text, and code in one file. And I will just show you that without any real Atom Probe data, because I will just show you with some. Thanks, David Sexy, for changing some of the reader issues. So apparently now, if we move our code out to a lot of different people, we're seeing errors now that we haven't seen before. So maybe that's great now. Maybe it was a good idea to call our toolbox release 0.9, so we can fix all of that for 1.0. Anyway, so just to give you a very quick intro, for example, if you want to make a script that does a certain task, you would probably start with some title for it. For example, plotting a sine wave. Yeah. Plotting a sine wave, and you can actually change that to title. This is plotting a sine wave, and you can explain this script plots a sine wave. And then you can start inserting code. And for example, you can create a variable x that is 1 to 2 times pi. And you can see you get very nice code completion in the live editor. I don't know why the code completion isn't as good in the main Matlab workspace yet, but it's very good in the editor. And then we could go y equals sine of x. And I could go and run that code. And now you can see that code also dumped everything in the main workspace. So it's not. So you're actually working with. You're actually working in your main workspace. So you can pull things out of your workspace into your script and work with them. And the other way around, you can dump things into your workspace. Once we have done that, we might want to go and plot x, y, and rerun the script. Or we could put a section in there, so we could go and put a section break in between. So now this would be code to. We can put a comment in. So comments start with %signs. Code to create the data. And here would be code to plot data. Up, and we probably want to make that into a comment. And now I can just run either the, let's make it a little bit wider. So now I can run the entire code, or I can run just the section, okay? Oh, and probably 1 to 2 pi, and probably I want to do that in 100 steps. I think that would work like this. No. I usually use the linspace command. And then we can run the section. Okay, let's do it in the so I want to go from 0 to 2 times pi, and I want to do that in 100 steps. So sorry, some of the Matlab syntax, even after all these years, it's not 100% familiar to me. And now we've got a plot like this here. And the reason why I wanted to quickly show that to you is because it's a very powerful way to create scripts, and we will use that quite a lot. And then to use it for documentation. Because if you go here to view, you can go and hide the code, for example. And you can have the output inline or output on the right. So the default was output on the right. And here we can have the output inline and hide the code, for example, or show the code. And then you can go and save the file as a PDF, as a Word document, as HTML, or as LaTeX. So if you save it as a, and this is really great for reporting. So essentially, when you analyze your Atom Probe data, even if you work in the command line, you can just copy the commands you had in the command line into a script, and then rerun your entire analysis. And then save the save it as a PDF, Word, or as a LaTeX file, and either add that to your paper as supplementary materials, or just document your entire analysis that way. And this is really what we use heavily, that you do your analysis in the command line, but you copy all of your commands in your Livescript. And then once you're done with the analysis, you can rerun it for different data sets, and you can save it and give it to a reviewer. You can save it and add it to oh, thank you, Sabine. Obviously, you know the so my student Sabine just said, okay, this would be the right way to create 100 steps of X in order to do a 2 pi plot. But I think this was not the main reason why we did that here. Anyway, it was just me showing to you how that works. And if in the Getting Started guide, you will find a whole lot of those scripts. So first of all, you will find which functions are here. So right now, I've done most of that from memory, knowing which functions are where. And what you can see here is that we've grouped them essentially by what they work on. So if you work with ions, you have, for example, ions create complex, ions create isotope list, ions extract from mass spec. So for example, if I've still got my mass spec open, I could go and in the command window, what we've already done with the ranges extract from mass spec, I could go ions extract from mass spec. IT is just, I use it short for ion table. And then if I go ion and autocomplete, it can go extract from mass spectrum. And then all we need to know is which spectrum we want to extract it from. And then we get a list of which ions we have defined in that mass spectrum. And this is maybe a little bit different to what we've had so far in Atom Probe. So far we've only defined ranges. We define ranges and ions. And the reason for that is obviously we want to give you a platform to develop advanced mass spectrum analysis, for example, to calculate mass spectral overlaps by knowing, which ions we have in there. So you can take the natural abundance from our abundance table and calculate which ions or what number of ions would be missing. And Valentin already wrote, of course, that the ions extract from mass spec only works if you already have ions defined, which in the other mass spec that we had just popping up, there are no ions defined yet, so you can't find any of those out. If I go and for that mass spectrum look at the children, so we had children. Oops. Did I? It should have quite a lot of children. Why does it have? Oh no, the mass spectrum doesn't have. Sorry. If I go on the axis that spectrum is in, spec dot. This is the spec dot parent, and if I look at the children of the parent, so the children, then you'll see this is all of the things that we have defined in this mass spectrum. So we have all of the area plots are our ranges, and you can see all of the ranges have isotopes and charge states defined with them. And all of the stem plots are the ions. So you can see we've got a stem plot for silicon oxide 2+, for magnesium+, vanadium 2+, and so on and so forth. And this populates this entire plot here. But I'm not going to dive too deep into that. This is actually something that Martina will be talking about in the next session. And with that, I actually will conclude the first session. And we will have a short break. Let me just have a look at the program. So now we're going until 10:30, and then we'll have a half an hour break until 11 o'clock. And then Martina will start with the mass spectrum, ion definitions, and ranging. So then we will show you in depth about how to build up a mass spectrum like this. And how to then also come up with a basic plot of your Atom Probe data. Just very quickly, we'll go into that in depth later on. And this should set you up for concentration calculations, concentration plots, and so on and so forth. So with that, I want to ask you: are there any questions for the first part of the Atom Probe School? So what we can do is I will just maybe take the entire everything that I've done right now and copy that into the group chat, and I will also open a new file here, and we'll give you all of that code later on via email as well. So if you've got any questions, can you just raise your hand and we will unmute you so you can ask your questions, or you can ask your questions also in the chat. But I think for now this was all relatively basic. I think, yeah, Markus? Give me a second because Yes, I can hear you, but the people will not be able to hear you.
No worries. No. Okay, it's good. Okay, it's good, Peter. It's going really great. Very helpful.
Okay, I've just seen that on this screen I have not added the system sound, so let me just.
I think they all can hear. Also Markus Peter.
Hmm?
I think all the people can hear Markus Peter.
Yeah, but people can hear Markus through Zoom. Yeah, that's correct. Yeah.